Hello, I am Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So, in your power electronics and drive class, so we have started three-phase converter, AC to DC converter. Though actually we are supposed to discuss about three-phase full-wave converters, but to start with, we have started our discussions with say why three-phase converter, what is its advantage, where it is applicable, and what is its application over advantage over the single-phase converters. So, and with these discussions, we have started the three-phase converters, its classifications, particularly half-wave converters like 3 pulse, 6 pulse, and for full-wave converters, that is 6 pulse and 12 pulse converters. Oh, and we have discussed three-phase half-wave converters, its circuit diagrams, waveforms, output voltage expressions, RMS value of the output voltage, and also we have discussed the waveforms of the output voltage for a different trigger angle for different load type of loads, say for RL load and resistive loads, etc. We have discussed these waveforms for RL load, that is for trigger angle at 30 degree, say 60 degree and 90 degree for RL load. And for resistive load also we have discussed the waveform, output waveform, voltage waveform, that is for trigger angle at 0 degree, 15 degree, 30 degree, 60 degree, and so on. In the next class we will discuss about the three-phase half-wave converters with resistive load or RL load with freewheeling diode. So to derive an expression for the average or DC output voltage of a three-phase half-wave converter with resistive load or RL load with freewheeling diode. So in this case, actually a three-phase half-wave control rectifier with resistive load, thyristor T1 is triggered at omega t equal to 30 degree plus alpha, and the thyristor 1 conducts up to omega t equal to 180 degree, that is equal to pi radians, and when the phase supply voltage that is VAN, that is A phase, decreases to 0 at omega t equal to pi, the load current falls to 0 and the thyristor T1 turns off. So this is natural commutation. So, and the T1 conducts from omega t equal to 30 degree plus alpha to 180 degree. So for resistive load, so actually we can find out this average DC output voltage for this three-pulse converter, that is three-phase half-wave control rectifier, is calculated by using this equation. So VDC equal to 3 by 2 pi, and this integration over alpha plus 30 degree to 180 degree V0 d omega t. And you know this output voltage V0 that is equal to say instantaneous voltage VAN would be equal to Vm sin omega t for omega t equal to alpha plus 30 degree to 180 degree. That is actually shown here also in our earlier say waveform like this. Okay, so like this. Okay, actually if we take this into consideration, so and putting this value, so calculating it over integrating it over alpha plus 30 degree to 180 degree, so sin omega t d omega t. So this is the integration of sin omega t equal to minus cos omega t, and it is limit is from alpha plus 30 degree to upper limit is 180 degree. Now if you put this limit, so upper limit minus the say lower limit in the expression, so it will be So before minus is there, so it will minus cos 180 degree, and this minus and minus will be plus cos alpha plus 30 degree in case of for omega t. So VDC will come like this, 3 Vm by 2 pi minus cos 180 degree plus cos alpha plus 30 degree. And you know cos 180 degree, it is actually minus 1. So we get that will be equal to, so minus 1 is plus 1. So the 3 VDC equal to 3 Vm by 2 pi 1 plus cos of alpha plus 30 degree. So this is the expressions of the say resistive load with DC output voltage, with resistive load or RL load with FWD, we can do that. So in this way. Now we'll discuss about three-phase semi-converters. So semi-converter means actually we have to say reduce 3 thyristors with 3 diodes. So basically three-phase semi-converters are three-phase half-control bridge control rectifiers with 3 thyristors and 3 diodes connected in the form of a bridge configuration. So 3 thyristors are controlled switches which are turned on at appropriate times by applying appropriate gating signals, and the 3 diodes conduct when they are forward biased by the corresponding phase supply voltage. Okay, so three-phase semiconverters are used in industrial power applications up to about 120 kilowatt output power level, where single quadrant operation is required, and the power factor of three-phase semiconverter decreases as the larger as the trigger angle alpha increases. The power factor of a three-phase semiconverter is better than three-phase half-wave converters, and so that's why it is applicable up to 120 kilowatt of output power level. So this is actually the figure shows a three-phase semiconverter with a highly inductive load, and load current is assumed to be constant and continuous in nature with negligible ripple. So this is the circuit diagram like this. So actually it will be like this. Okay, actually in this way. Okay. So actually this will be like this. This will be like this. So actually the thyristor T1 is forward biased when the phase supply voltage VAN, this one is positive. This is positive and greater than the other phase voltages, this BN and say VCN. So these are phase voltage and these are the line voltage. So VAB, that's it is a line voltage between A and B. BBC line voltage between say B and C. BCA line voltage between C and A. But VAN or VBVN or VCN is the phase voltage. Okay. Actually. So when T1 is forward biased, when actually this this phase voltage VN is greater than the other two phase voltages VBN and VCN, and in this time diode D1 is also forward biased. So D1 is also forward biased when the phase supply voltage VCN actually VCN is more negative than the other phase supply voltage. So this is for, so actually, so in that case this will be like this. So this will be like this, the power flow diagram, current flow. Thyristor T2 is forward biased if VBN is positive and greater than the other phase voltages. This VBN is positive and greater than the other phase voltages, then thyristor T2 will be in conduction, and in that case this diode D2, actually this will be this diode D2 will come in conduction if it is forward biased, and when the phase supply voltage N is more negative than other phase supply voltage. So in that case the path will be like this. So this is the current flow path. And thyristor T3 is forward biased when say phase voltage VCN is positive. So this is positive, and it is greater than the other phase voltages, and diode D3, actually this diode D3 is more negative. The diode D3 is forward biased when the phase supply voltage Vn is more negative than the other phase supply voltage. So as a result, so this will be like this. Okay, this will be like this. So this is actually current flow path, and this figure actually shows the waveforms for the three input supply voltage, three phase input supply voltage, and the output voltage, and the thyristor and the diode current waveforms, and the current through the freewheeling diode. This is the freewheeling diode DM, and the supply current IA for A phase. Actually this is the supply current IA. Okay, and the frequency of the output supply waveforms is 3 time supply frequency 3 fs. This is the input AC supply frequency, and trigger angle alpha can be varied from 0 to 180 degree. So so in this way, so during the time period pi by 6, omega t is in between from pi by 6 to 7 pi by 6, that is from 30 degree to 210 degree. Thyristor T1 is forward biased. See, this is actually up to this. Thyristor T1 is forward biased. And in that case, if thyristor T1 is triggered at omega t equal to pi by 6 plus alpha, so thyristor T1 and D1 conduct together, and the line to line supply voltage VAC appears across the load, and at omega t equal to 7 pi by 6, VAC starts to become negative. So basically this here the VAC starts to negative, and as a result, so this is VAC. So VAC actually starts to negative, and the freewheeling diode DM turns on and conducts. Okay, and the load currents continues to flow through the freewheeling diode DM, and the thyristor T1 and diode D1 are then turned off. Okay, so basically this is shown here. See, this is VN, which is the difference between this VN equal to VAC plus VCN. Okay, so actually this is the supply phase voltage, and this is actually defined. This is the conduction. Okay, and this is output voltage. Okay, and this is actually the current through the diode thyristor 1 and diode 1, IT1 D1, and this is for IT2 and ID2. This is thyristor 2 and diode 2, and this is thyristor 3 and diode 3, and for each time and this is the diode current, freewheeling diode current. Okay, so this is actually the load current IA. Okay, so this is Actually, this is for waveforms for alpha equal to 90 degree. Okay. Actual it is shown here. So from this period, so thyristor T3 and D3 is in operations. So from this period, thyristor pi by 6 plus alpha to it is actually 7 pi by 6 thyristor D1 T1 and D1 is in operations, and from this period, so 7 pi by 6 to up to this time, so freewheeling diode is in operations, and again from say likely a process is repeated for this is thyristor 2 and diode 2, then again freewheeling diode, then thyristor T3 and D3, then again freewheeling diode will be in operations, and in this way this output voltage waveform and the current to thyristor 1 and diode 1, then thyristor 2 from diode 2 for conduction, so it is shown, and for thyristor 3 and diode 3, and this is the say waveform for the current for freewheeling diode. Okay, and this is your output current for phase angle of 90 degree. So if the freewheeling diode DM is not connected across the load, then thyristor 1 would continue to conduct until the thyristor T2 is triggered at omega t equal to 5 pi plus 5 pi by 6 plus alpha. Okay, and the freewheeling action is accomplished to thyristor 1 and D2 when D2 turns on, as soon as VAN becomes more negative at omega t equals 7 pi by 6, and if the tubular angle is less than equal to pi by 3, each thyristor conducts for 2 pi by 3 radians, that is 120 degree, and the freewheeling diode DM does not conduct. And so the waveforms of the three-phase semiconductors with alpha less than equal to pi by 3 is shown in that figure. Okay, so this is the figure. Once again, I am repeating this three-phase semiconductor circuits and waveforms. So this is the circuit diagram. So this is the three-phase supply and connected across this bridge converters, which is consisting of 3 thyristors and 3 diodes, and the load is highly inductive in nature, and a freewheeling diode is connected across the load. So DM is the freewheeling diode. Now when thyristor T1 is forward biased, and actually the supply voltage phase voltage VAN is positive and greater than the other phase voltage VBN and VCN, then the diode D1 is also forward biased, and the three-phase supply voltage VCN is more negative than the other phase supply voltage. Then the current flowing part will be like this. Okay, so this will be like this, clear. And when thyristor T2 is forward biased, when phase supply voltage VBN, actually this one is more is positive and greater than the other phase voltages, and then diode D2. The D2 is forward biased when the phase supply voltage VAN is negative than the other phase supply voltage. So this will be like this. Okay, this will be like this. Okay, and thyristor T3 is forward biased when phase supply voltage VCN is positive with and greater than the other phase voltages, and diode D3 is forward biased when the phase voltage VBN is more negative than the other phase supply voltage. So this will be like this. Okay, as I told you. So and this is the current part. Now this the waveforms shows for the three-phase input supply voltage, the output voltage, the thyristor and diode current waveform, the current to the freewheeling diode DM, and the supply current IA. So the frequency of the output supply waveforms is 3 times input supply frequency, and the trigger angle alpha can be varied from 0 degree to 180 degree. So actually this is during pi by when omega t is in between pi by 6 to say 7 pi by 6. Actually that is from 30 degree to 210 degree. Thyristor T1 is forward biased, and if thyristor T1 is now triggered as omega t equal to pi by 6 plus alpha, that is here. So this thyristor T1 and diode D1 conduct together, and the line supply voltage VAC, that is VAC, which is nothing but the difference between the VAN and VCN, is say appear across the load, and at omega t equal to 7 pi by 6. So VAC say start negative. So it is at here it is start negative, and as a result and the freewheeling diode DM turns on and conducts. So at here, so freewheeling diode, this is the current, so freewheeling diode will turns on and conduct. Okay, and the thyristor T1 and diode T1 so turns on and conducts, and the load current continues to flow through the freewheeling diode DM, and thyristor T1 and diode D1 turns off. Here it is, see this thyristor T1 and D1 already say turns off at say alpha equal to say 7 omega t equal to 7 pi by 6. So as a result this is the current through this freewheeling diode will flow, and this current will be like this. This is the supply current. Okay, now if the freewheeling diode DM is not connected across the load, then thyristor 1 would continue to conduct until thyristor T2 is triggered at omega t equal to 5 pi by 6 plus alpha. That is here. That is here actually. Thyristor 2 is in conduction. Basically, this will give you the current through thyristor 2 and diode D3. Okay, and say and freewheeling action is accomplished. In that case, will be from if freewheeling diode is not connected, actually then thyristor 1 would continue to conduct until thyristor T2 is triggered at omega t equal to 5 pi by 6 plus alpha, and the freewheeling action is accomplished to T1 and D2. And when D2 turns on, as soon as say phase voltage VA1 becomes more negative at omega t equal to 7 pi by 6, and if the trigger angle is alpha is less than equal to pi by 3, each thyristor conducts for twice pi by 3 radians, that is 120 degree, and the freewheeling diode does not conduct. And the waveforms for a three-phase semiconductor with alpha less than equal to pi by 3 is shown here. So this is the waveform. Okay. So that what I told, that is say described in this waveforms. So clearly you will get how the output voltage and the waveforms of the thyristor 1, that is IA current, that is supply current. This is due to the diode 2, and this is the due to thyristor 2. This is due to diode 3, and this is due to again diode 1. This thyristor 3, then diode 1, and then actually this is the current waveform. Okay, so we can define this three line to neutral voltage, that is three-phase voltage, as follows. That is VRN, which is nothing but the VAN, which will be Vm sin omega t, and Vm is the maximum phase voltage. So, and VYN, that is nothing but VBN, will be Vm sin omega t minus 2 pi by 3, that is omega t minus 120 degree, and VBN, actually this is equal to VCN, which will be equal to Vm sin omega t plus 2 pi by 3, that is Vm sine omega t plus 120 degree, or you can say this is Vm sine omega t minus 240 degree. So the corresponding line to line voltages are that is VRV is equal to VAC, that is which is the difference between VAN and VCN, the phase voltage of the A phase and C phase. So this will be equal to root 2 Vm sine omega t minus pi by 6. VYR, that is equal to VBA, which is nothing but the difference of B phase voltage and A phase voltage. So this will be equal to root 3 V m sine omega t minus pi by 6, and VBY, so this is equal to VCB, that is equal to VCN minus VBN, which will be equal to root 3 Vm sine omega t plus pi by 2, and VRY equal to VAB equal to VAN minus VBN, so equal to root 3 Vn sine omega t plus pi by 6, and Vm is the peak phase voltage of a star connected source, and these are explained here in this waveform. So yeah, you can get if you say mathematically express the expression is coming from this say waveform diagram also. So you can jolly well find out the output voltage, the different say current conduction, that is through resistor 1, diode 2, resistor 2, diode 3, resistor 3, and diode 1, then the supply current. Okay, so that is about this without freewheeling diode, and we can find out the expression for the average output voltage for the three-phase semiconductor for alpha greater than pi by 3 and discontinuous output voltage. For alpha greater than equal to pi by 3 and discontinuous output voltage, the average output voltage is found VDC equal to 3 by 2 pi. So it is from pi by 6 plus alpha to 7 pi by 6 integration over also VDC d omega t. And if you say integrate and put the limits here, so you will get this VDC equal to 3 root 3 Vm by 2 pi into 1 plus cos alpha, or VDC equal to the 3 Vml by 2 pi 1 plus cos alpha, where the maximum average output voltage that occurs at the delay angle alpha equal to 0, and that will be here. So it is will be 3 root 3 Vm by pi, and normalized average output voltage will be so VDC by VDM, that will be equal to 0.5 into 1 plus cos alpha. So RMS output voltage is found from these expressions, that is 3 by 2 pi integration over pi by 6 plus alpha to 7 pi by 6. So 3 Vm square sine square omega t minus pi by 6 d omega t to the power half, that is root. So and expressions becomes the RMS value of the output voltage will be root 3 Vm after say calculations and putting the limit, we will get it root over 3 by 4 pi into pi minus alpha plus half sine 2 alpha. And for alpha less than equal to pi by 3 and continuous output voltage, so if we put this, so VAB will be equal to root 2 Vm sine omega t plus pi by 6, for omega t equal to pi by 6 plus alpha to pi by 2, and output V0 equal to VAC will be root 3 Vm sine omega t minus pi by 6, for omega t equal to pi by 2 to pi by 6 plus alpha. And the average DC output voltage is calculated by using the equation. So VDC equal to 3 by 2 pi from integration over pi by 6 plus alpha to pi by 2 VAB d omega t plus integration over pi by 2 to 5 pi by 6 plus alpha say VAC d omega t. And if we calculate this, so VDC equal to 3 root 2 Vm by 2 pi into 1 plus cos alpha, and V normalized value of this value Vn equal to VDC by Vm, so that's what will come to 0.5 into 1 plus cos alpha. So the RMS value of the output voltage is calculated by using these equations. That is uh, G output RMS value of output voltage of G O RMS equal to 3 by 2 pi integration over pi by 6 plus alpha 2 pi by 6. So G AB square d omega t plus integration over um, actually pi by 2 to 5 pi by 6 plus alpha equal to into v square vac square d omega t, and that will come into the result of say output RMS value will be root 2 vm 3 by 4 pi twice pi by 3 plus 3 cos alpha to the power half. So basically, these are the simple mathematical calculations of calculation. Say, um, and in some cases, some trigonometric relationship are being used to find out these values. So that is DC output voltage, RMS values of the output voltage, etc., and the normalized voltage, normal voltage Vn actually for alpha pi by 3. So with this we can say complete discussions about three-phase half-wave converter at a different load, resistive inductive load, and with freewheeling diode, and what will be the shape of the waveforms, the modification of the waveform in absence of the freewheeling diode is also being discussed. And also we have calculated the values of output voltage for discontinuous current mode and for continuous current mode, or that is discontinuous output voltage and continuous output voltage we have calculated. So that's all about this three-phase half-wave converters, and hope you have understood it. You will go through it